Good morning, everyone. In today's class, we'll discuss electromagnetic waves. So, what is actually the meaning of electromagnetic waves? So, you are aware about the fact that electromagnetic waves are nothing but the waves which are composed of electric and magnetic fields, and these electric and magnetic fields are orthogonal to each other. So, such type of waves are known as electromagnetic waves, or in a simple way, the oscillating electric field and the magnetic field. And since they are perpendicular to each other, such type of oscillating magnetic and electric field is known as electromagnetic wave. So now this is the important phenomena which is important for the study of the interaction of electric and magnetic field. So the electromagnetic field is a non-mechanical wave, and the special character of this electromagnetic wave is that it doesn't require any material medium to travel through which. So so that is the reason that we say that the electromagnetic wave can travel not only in the air but also in the vacuum also throughout this space. So now with this particular fact, we just move forward to our today's chapter, that is the electromagnetic waves, and what are the mathematics involved in understanding the character of electromagnetic wave we just see in today's class. So in today's class, it is an introduction to the electromagnetic wave. That is the reason that we just start our today's class with a short video about the history of the electromagnetic wave, right? So here we just discuss the electromagnetic wave.
Scottish physicist James Maxwell. In an historic set of equations, Maxwell had theorized that visible light was an electromagnetic disturbance with a specific wavelength, and that other electromagnetic waves existed as well. In 1886, Hertz noted tiny sparks jumping from a discharging induction coil to another coil nearby. That seemed to indicate the presence of electromagnetic waves. With his assistant, he set about systematically investigating the phenomenon and constructed an apparatus comprising a kind of transmitter on the left and a receiver on the right. Hertz edged closer to the transmitter. At a distance of about 2 meters, sparks started to jump across the gap between the receiver's conductors. And Hertz was sure he knew why. The sparks were the result of invisible electromagnetic vibrations, which were radiating like waves through space and energizing the receiver. Helmholtz was the first to be informed of the sensational results. His comment, "Bravo." It was Helmholtz, too, who published details of the experiments. Hertz continued his research with patience and vigor. On one occasion, he wrote to his parents,
"I'm working like a factory hand, repeating every step 1,000 times over. I spend hours on end drilling one hole after another."
He sent regular progress reports to his father, who was by then a member of the Hamburg Senate. If it was true that electromagnetic disturbance took the form of a wave, it should also be susceptible to reflection and interference. At the end of 1888, Hertz set up another experiment in the lecture theatre at Karlsruhe. His aim this time was to show that electromagnetic waves could be bounced off a metal reflector. The entire length of the room was needed for the experiment because Hertz's apparatus, the transmitter on the left and receiver on the right, could only produce radio waves with a wavelength of around 60 centimeters. A sketch showing how the apparatus should be arranged in the room. Benches at the rear served as supports for the 2-meter-high zinc reflector. The experiment had to be conducted in darkness to enable the scientists to make out the faint optical phenomena at the receiver. Sometimes Hertz and his assistant found it took hours for their eyes to adapt to the dark. The transmitter was switched on. The electromagnetic waves struck the zinc plate and were reflected, at an angle equal to the angle of incidence, back to the receiver. Then, Hertz's assistant stepped into the path of the beam. His body absorbed the waves and spark action at the receiver ceased. In this and later experiments, Hertz confirmed the characteristics of electromagnetic waves. One characteristic, which is very important today, is interference, which can either disturb or reinforce radio or TV reception. A wave reaches our aerial. We receive a signal. It's joined by another wave, an indirect or reflected wave perhaps. If the two waves are in phase, reception is improved. But if they're out of phase, they cancel each other out and reception is severely impaired. But back to their discoverer. Now a scientist of international renown, Hertz moved in 1889 to Bonn University. Here he finished writing the scientific papers subsequently published under the title The Principles of Mechanics. Hertz himself, however, didn't live to see their publication in 1894. He died shortly before his 37th birthday of insidious septicemia. From his deathbed, he wrote to his parents,
If anything should happen to me, do not mourn. Be proud and think of me as one of the chosen few who live but briefly, yet long enough.
Science paid tribute to Hertz by naming the SI unit of frequency after him. 1 Hertz means 1 cycle per second. Ordinary alternating current from the mains has a frequency of 50 Hertz, which corresponds to a wavelength of 6,000 kilometers. Low-frequency waves are 10 times shorter. Next in the spectrum are radio and television frequencies, followed by radar in the microwave band and heat radiation in the infrared range.
Now, I think that you understood what is actually the history of electromagnetic waves and how this frequency unit has been.
Sometimes while writing my newsletters, I tend to type so fast that there are spelling for a while now, and it's
Now you are having the information, right? What is actually the history of the electromagnetic wave, and now we'll see the is basic equations of the electricity and magnetism. So the first basic equation, or we just say that in the examination we'll ask you write the basic equation of electricity and magnetism, and also write the Maxwell derive the write the Maxwell's basic equations, right? This will be the questions. This two questions are having the same answer. So you can just see that the first equation that is related to your basic equation of electricity is the Gauss law. So what is this actually? Gauss law is all about. So Gauss law is nothing but it is given as the integral form of this Gauss law is given by E into ds is equal to q by epsilon naught. Now q by epsilon naught. Now what is actually this means, right? This means that the electric flux, right? Theoretically, we just say the sentence wise, we just say that the electric flux. See the electric flux through a closed surface. So when you say the flux is nothing but the number of lines, either it may be magnetic lines or the electric lines, right? So here, since we are talking about electricity, so the here we just call that as electric flux. So the electric flux through a closed surface, through a closed surface, through a closed surface is equal to is equal to is equal to 1 by epsilon naught times 1 by epsilon naught times the net charge, the net charge, the net charge, the net charge enclosed, the net charge enclosed by the surface, by the surface is 0. Now this is the what you can say theoretical statement of the Gauss law in electricity. The electric flux through a closed surface is equal to 1 by epsilon naught times the net charge enclosed by the surface, which is equal to 0. Now this is the basic electricity equation that is invented by Gauss. So just say that is called Gauss law. Now the next important equation which is related to magnetism is your second one important is magnetic flux. That equation is known as again B into ds, right? Right. Now this is given as integration of B into ds, which is equal to 0. Now this is equation number 2. So which says that magnetic flux through a closed surface is equal to 0. So the theoretical statement sentence is nothing but magnetic flux through a closed surface, through a closed surface, closed surface is equal to 0, is equal to 0, right? Now this is the second law, and the third law is nothing but law of, we also say that Faraday's law of electromagnetic induction, which is given as integration of B into di. So here you should note that this integration, we are having this circle, it means it is a closed surface, right? So here B into di is equal to mu naught I. This is actually Ampere's law, so which says that the electric field is produced by magnetic field uh, is due to steady current. Ampere's law, this is Ampere's law. So actually this should come under fourth one, but since you can just change it to either way, so Ampere's law, this is called Ampere's law for magnetic field due to magnetic field, right? This is due to magnetic field due to steady current, right? this is for steady current. So what will happen if the current is not steady? So definitely we'll just deal with that is called displacement current. So in the next class we'll just see that what that particular law which has been modified by Maxwell, right? This Ampere's law has been very modified by Maxwell for changing current, right? Now this is for steady current. So for the steady current, the integration of B into di is equal to mu naught I. That is called Ampere's law for magnetic field due to steady current. Now this law has been also modified by Maxwell. That is, if the current is not steady, right, it is definitely for varying fields. So you'll find that that is known as displacement current. So that displacement current concept was given by the Maxwell, right? So we just see. So the next uh, law is the law of Faraday's law of electromagnetic induction, which says that the change in the magnetic field will be, or the electric field is actually produced by changing magnetic field, right? Okay, just write dB d4 by, right? This can also be written as right. Now we just see this this particular concept. We just see this one with respect to d5, right? Now, uh, now that is called Maxwell law of Faraday's law of electromagnetic induction. So Faraday law of electromagnetic right, electromagnetic induction, which says that so the Faraday law of electromagnetic electromagnetic induction says that electric field is actually produced by the see it is produced by the electric field is produced by changing magnetic field. So we just say that is called the uh, electricity law of Faraday's law of electromagnetic induction. Right now, what we can do here is that so in order to understand this very clearly, now let's see, this can be Faraday's law of electromagnetic induction. The mathematical relation is given by this can be this is given by right, integration of E into di, right, E into di, which is equal to minus dou phi by dou phi b by dou t. Now this is electric field, is what you can say electric field. This is the fourth Maxwell equation. The electric field is produced by so electric field is produced by changing magnetic field. You can just see the LHS and RHS. By means of this LHS, you can easily understand that the electric field is produced by changing magnetic field, right? So now we need to understand this what is happening to Ampere's law, modification of Ampere's law, which is done by see modification of Ampere law, which is also known as, we say that is called displacement current, right? So Maxwell has done the modification of Ampere's law, and since the Ampere's law is valid only for the steady current, so what will happen if the current is varying? So Maxwell suggested that the total current and propose that the magnetic field is produced by changing electric field, and this is valid for steady state, that is Ampere's law. Thus, the changing electric field is equal to current which flows as long as the electric field is changing and produces the same magnetic field. And this ordinary conduction current is also known as the displacement current. What it means actually, it means that as the your current is changing, right, your the magnetic field will also change in the same fashion. So we'll just say that is called the conduction current or the displacement current. So mathematically this is proved by Maxwell. So what he has done is that he has considered, so he considered, let us consider, in order to modify this Ampere's law for varying current. So he considered, see what he has considered. So let us consider the parallel plate capacitor. He has taken a parallel plate capacitor, right? So parallel plate capacitor for changing field, right? Since the Maxwell modified for changing field, so for changing field, so we'll write that as changing field. Clear everyone? Now we have just taken a parallel plate capacitor for changing field. So electric field is given by, we are having the information from the intermediate, the electric field. So by using the intermediate knowledge, we are just writing that electric field is given by, for changing right field is given by, is equal to actually E is equal to Q by epsilon naught A, right? Now employees, now you already uh, having the information, right? This is for changing electric field, right? This is the E is equal to Q by epsilon naught. So when you just differentiate this equation, now differentiating, we'll write the C, differentiating 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 why? Because we need to know the changing field, right? Changing electric field. So differentiating E, right, with respect to t, we'll just see what will happen if we just integrate, if we differentiate E with respect to t. So what it will be, dou E by dou t, which is equal to epsilon naught, that as it is, right? 1 by, we'll write constant, right? Epsilon naught is a constant, A is the area, right? And the you already had the information, right? This dq by, this will be dq by dt. And what is dq by dt? Since dq by dt, the rate of change of the charge is nothing but current, right? I think that you are aware of this fact, that the rate of change of charge is nothing but it is current, right? So therefore now our equation dou E by dou t will be equal to I by epsilon naught into A. So what it means that this is now we just write this I can also be written as what you will write, epsilon naught A into dou E by dou t. Clear everybody? Now, so therefore, here the displacement current, here I is nothing but, we can write the I instead of I suffix D, which is reference to the displacement current, right? We say that, so the displacement current with the changing, for changing field is given by I is nothing but epsilon naught A into dou E by dou t. This is called the modified form of Ampere's law. So the modified Ampere law can also be written as, so you can just see this modified Ampere law. So the modified Ampere law can now be rewritten as integration of B into di, which is equal to mu naught instead of I. So I plus, here the modification is addition, right here. So I plus ID. Now this is the modified Ampere law, which has been discovered by the Maxwell, right? So with this, what you can say that we have just come to the end of our first class. So in the first class, we discussed about the basic laws of Maxwell's equation, which is also known as the basic laws of electricity and magnetism. So, and also we discuss about the displacement current, how the Maxwell has modified the Ampere's law. So actually Ampere's law is valid only for the steady current, but Maxwell came to the conclusion that, okay, this is for steady current, right? What will happen if the current is varying? So for varying current, he has considered the parallel plate capacitor, and we already having the information, right? The electric field is given by the formula capital E is equal to Q by epsilon naught A. So by differentiating E with respect to T, so dou E by dou T is equal to 1 by epsilon naught A dou Q by dou T. Since the rate of change of charge is nothing but current, so dou E by dou T is equal to I by epsilon naught A. I is nothing but epsilon naught A into D dou E by dou T. So instead of I, what we can write, since it is a displacement varying current, so I suffix D is equal to epsilon naught A dou E by dou T. This is the modified Ampere's law. So integration of closed loop, closed surface B into di is equal to mu naught into I plus it. So with this, we can just again we'll meet on the next class. Thank you everyone. Thank you for your patience for understanding this particular concept. Understood. So we'll just end our today's class. Again, we'll just meet in the next class, right?